Okay, maybe in the interest of time, we should get started. Good morning, everyone. I guess good afternoon to people on the East Coast. We are going to start our VCO today. The VCO stands for the Virtual Consulting Office, and essentially it's kind of an informal way for us to interact and share kind of the things, the progress that have been made in iGuide and the associated community. So that's what we are going to do today. For those of you who don't know me, my name is Anand Padmanabhan, and I'm a research associate professor in the Department of Geography and Geoscience at the University of Illinois Urbana-Champaign, and I'm serving as the managing director for iGuide. And it is my distinct pleasure and honor to introduce today's speaker, Dr. Yuelin, and she is assistant instructional professor in geographic information sciences in the division of social sciences at the college at the University of Chicago. So her research is on geocomputation and geospatial data science, digital privacy, and she did her PhD from the Ohio State University under Professor Harvey Miller. So today she's going to be talking to us about geoprivacy, which is really an important topic for us and as iGuide, as well as for the community, because this is something that we need to really pay attention to. And so it would be great to hear from you, Lynn, on this topic today. And she's also presenting in terms of kind of the in certain collaboration aspects that she did with iGuide with the UCGIS as a part of a UCGIS community champion. So this was one of the works that she did. So we are proud to have her here and happy to hear from her. Yeah, the floor is yours.
All right, thank you, Anand, for your introduction. And hello, everyone. Thank you for joining our webinar. I'm Yuelin. I am assistant instructional professor at the Center for Spatial Data Science at the University of Chicago. So today I'm happy to be here and share my research with you on location privacy and ethics in spatial data science. So my research in this area is originated from my interest in the new disclosure avoidance method applied in the 2020 United States Census. Specifically in 2020, the Census Bureau applied a new method based on an emerging privacy principle called differential privacy to avoid disclosing personal information about census respondents. Differential privacy ensures that adding, deleting, or editing any individual's information will not alter the aggregated statistics in census tables significantly, and therefore it would be hard for anyone to infer about an individual's information from census data. So there are several reasons why privacy protection is important in the perspective of the Census Bureau. Confidentiality is the first reason because it is a major determinant of whether people choose to respond to the census or not. So the Census Bureau wants to demonstrate that they are able to provide a strong privacy protection for the data so that eventually they can ensure a high response rate to the census. And the second reason is probably more important because ensuring that census data cannot be used to identify any individual is a legal requirement by the Title 13 of the US Code. So to maintain a high response rate and to meet the federal law's requirement, the Census Bureau has been working for decades to improve their privacy protection methods. Again, in 2020, the Census Bureau used a new privacy protection method based on differential privacy to protect the census data. And this decision was made based on a database reconstruction experiment that conducted a few years ago. In disclosure avoidance, there is a database reconstruction theorem, which says that every time we release any statistic calculated from a confidential data source, we leak a small amount of private information. And if we release too many statistics too accurately, we will eventually review the entire underlying confidential data source. And in the case of census data, the Census Bureau has been publishing detailed statistics about different combinations of attributes, such as race, ethnicity, and so on. And these data are published at different geographic levels, such as census block groups, etc. So this has resulted in many, many statistics published by the census. In the 2010 census, for example, the data release contains approximately 150 billion statistics. So it is reasonable to be concerned that the census data can be used to trace back to the individual that provides the information. This concern was confirmed by the Census Bureau, where they found that using the 2010 data, they're able to reconstruct the block location and age for 46% of the US population, and 44% can be uniquely identified based on the location and the other attributes. So this finding has posed a major challenge and has motivated the Census Bureau to adopt a new privacy protection method in 2020. So besides census data, the use of other forms of spatial data has also raised location privacy concerns. One example is the spatial point data, such as patient locations. When we create maps for these type of data, a common practice is to reduce the resolutions of the maps for privacy protection. But there are studies suggesting that even with low resolution maps, patient locations can still be easily reviewed using simple GIS operations. And another type of spatial data of concern is the human mobility data. So individual trajectories, for example, they're highly unique. So even when we remove the names and other personal identifiers for individuals in these kind of data sets, they can still be easily de-anonymized. So all these previous contexts leads me to think about the question, what are the good ways to protect location privacy for different forms of spatial data? And to answer this question, I designed a series of methods that consider the trade-off between privacy protection and data utility. And I'll talk about the trade-off in a few slides. So the Census Bureau's privacy protection methods have evolved from the whole table suppression in 1970 to data swapping in 1990, and to eventually to differential privacy in 2020. The privacy protection method based on differential privacy is called top-down algorithm. So this algorithm introduces uncertainty to census data for privacy protection. And specifically, it adds statistical noise to all census statistics from state-level geography to county, tract, block group, and block. And this is why this method is called the top-down algorithm. One major concern with the top-down algorithm is that it adds noise to all census statistics, which may be excessive beyond what's needed to prevent database reconstruction and protect respondents' privacy. And this excessive noise can further lead to unnecessary utility loss for census data and affects its application. Many studies have shown that the top-down algorithm introduces inaccuracies, especially for racial and ethnic minorities and geographic areas with small populations. As you can see on the bottom right, a large populations, geographic units with large populations remain mostly stable after applying the top-down algorithm, but smaller populations are significantly impacted. So there has been a lot of pushback from community activists and researchers who urge the Census Bureau to stop using the top-down algorithm. If you're interested in the impact of the top-down algorithm on census data, I created a tutorial on CyberGISX as part of my work for the iGuide Community Champion project that allows you to explore this kind of impact. So in order to mitigate the impacts on data utility while still preventing database reconstruction, we propose a new privacy protection method that explicitly optimizes or controls the utility loss. Specifically to avoid adding unnecessarily large noise to the data, instead of applying noise to all census statistics, we focus on those people who are at high risk of disclosure. So these are the people who are unique enough compared to their neighbors. For example, if you're the only one or two Asians in a white neighborhood, then you can probably be considered unique enough. So then the question is, how do we quantify unique enough? To resolve this question, we define lambda elements such that these can be fine-tuned as a hyperparameter. So once the lambda value is set, we will say that if lambda or fewer than lambda individuals share the same attributes in the geographic area, then these individuals will be considered unique enough and therefore at high risk of disclosure. So we developed two optimization models to relocate these individuals at high risk of disclosure to protect their privacy. The first model is called a minimum error model, where we relocate all the at-risk individuals while minimizing the noise introduced. And the second model is what we call the maximum protection model. So in this model, given a maximum amount of noise, which we also call the error budget, we will maximize the number of at-risk individuals being relocated to protect their privacy. So this is a diagram showing how our privacy protection strategies work. In this example, we set the lambda value to 1. So if there is only one individual with a certain attribute in a geographic area, we will consider them to be at high risk of disclosure. So here in geographic area B, there is an individual at high risk because they are the only people, they are the only person with certain attributes such as race, ethnicity, and so on. And for this individual, there are three possible ways to relocate them, which are indicated by the three arrows, 1, 2, and 3. So we determine the optimal relocation by using spatial optimization modeling, which minimizes or control utility loss while ensuring a certain level of privacy protection. And on the right, this is the privacy preserving data we eventually will get. So we compare the results of privacy protection methods with the top-down algorithm used in the 2020 census. This figure here shows the results of the minimum error model that relocates all at-risk individuals while minimizing the noise introduced. So on the privacy protection side, our minimum error model can relocate all at-risk individuals with a given lambda value, while the top-down algorithm does not guarantee that all at-risk individuals are being protected. So in this sense, we're able to offer stronger privacy protection to individuals who are the most vulnerable to disclosure. On the data utility side, our minimum error model introduces less noise to the data compared to the top-down algorithm, and even in geographic area with very small populations. So you can see it from here. So in summary, our minimum error model can effectively protect individuals who are the most vulnerable to disclosure while also introducing less utility loss to the data. So the minimum error model we just examined offers full protection to our data. But although this model introduces less noise compared to the top-down algorithm, if the noise required to protect all at-risk individuals still seems excessive, we can switch to our maximum protection model, which maximizes the number of at-risk individuals located given a maximum amount of noise, or what we call the error budget. So how do we determine this error budget? A key to make informed decision about the error budget is to be able to explore how privacy protection and data utility trade off. And here we use a multi-objective optimization model to explore this trade-off. So for this model, there are two objectives. The first one is to maximize the number of at-risk individuals being relocated, which is equivalent to maximizing the privacy protection. And the second objective is to maximize data utility of the privacy-preserving data. So in nature, these two objectives, they're conflicted in many cases, as you can see in this diagram here. So we are using an multi-objective optimization model to try to balance these two conflicting objectives. So we obtain a collection of optimal solutions that demonstrate the trade-off between privacy protection and data utility from the multi-objective optimization model. These optimal solutions maximize either privacy or utility when the other one is held constant. So here, an error budget can be determined by carefully examining different optimal solutions and impacts of these solutions on the data more locally. So here, for example, we show how the use of different solutions impacts population totals in each census tract, and there can be evaluations in terms of specific applications, such as disease rates for health or etc. So besides relocating individuals to protect privacy, we also explore using synthetic data to replace confidential data in census releases. Census microdata are extremely useful for research and policymaking when combined with secondary data, such as health records, criminal records, voting registration, and so on. But these data, they are mostly confidential and only available to certain researchers at secure federal statistical research data centers, which creates barriers for reproducible research and transparent policymaking. So one way to mitigate this problem is to release synthetic data as a substitute of the confidential data. Synthetic data, they are model statistical outputs closely resemble the format of confidential data and replicate the population's statistical and spatial distributions. For example, synthetic census microdata have the same set of attributes, such as age, ethnicity, race, and sex as the confidential data. But the value of these attributes are synthetic and created by statistical models. We develop an optimization approach to generate synthetic population microdata that can be aggregated to match the publicly available census tables. So this is a list of census tables that we choose, which includes a combination of the short form census variables such as ethnicity, race, sex, and age. The objective of the optimization model is to minimize the difference between the synthetic and the actual census tables. So based on the proposed method, we generate synthetic population microdata for over 200,000 block groups in the United States. And we compare the synthetic data with a 1% sample of the US microdata, which is the ACS public use microdata sample across all 2,351 PUMAs. So as you can see in this plot, we observe very high cosine similarity between these two data sets, with all the values above 0.6 and 63% greater than 0.95. And this means that our synthetic data are highly representative of the actual population distribution, both statistically and spatially. So besides census data, I also explore new privacy protection methods considering the privacy utility trade-offs for point level data. Such a trade-off is demonstrated in a 2021 paper by Kim and Kwan and more others. But in this paper, the authors review how geomasking home locations of patients for privacy protection introduces significant errors in travel times from homes to hospitals for these patients. So here, geomasking is a common approach to preserve privacy for point level data by displacing or aggregating the original locations of individuals to prevent re-identification. However, as suggested by existing research, common geomasking methods may substantially compromise the accuracies in spatial data applications. So another thing about existing geomasking methods is that most of them are based on a privacy principle called spatial k-anonymity. So this principle requires that each spatial point needs to be indistinguishable from at least k-1 other locations. And these will ensure that the probability of an adversary discovering the actual location of an individual to be at most 1 over k. So here we have an example of geomasking using random perturbation to achieve spatial k-anonymity. So here first, we draw a buffer around the point location that we want to anonymize to include at least k-1 other locations. And then we will displace the original point randomly within that buffer. So, however, spatial k-anonymity has limitations because it is only valid when the k-1 other locations, they are equally likely to be the actual location from the adversary's perspective. If the adversary has some side information about, for example, land use, real property parcels, and road networks that can be used to rule out some of the certain locations, then the assumption of spatial k-anonymity will be violated. And so these privacy guarantees provided by this principle will also be void. To address the limitations of existing geomasking methods in terms of privacy protection and data utility, I propose a method based on recent concepts called geo-indistinguishability. Geo-indistinguishability ensures that for any 2 points within a radius, the probability distribution of them being the true location will remain sufficiently close with any auxiliary data. So it can protect against anyone with any site information, regardless of whether it is currently accessible or it may be obtained in the future. So I formulate an optimization model to ensure that our method can satisfy the geo-indistinguishability constraint, while also minimize the expected distance displayed for privacy protection. So the method that we propose, which is called geo-indistinguishable masking, offers stronger privacy guarantee compared to spatial k-anonymity-based methods because it protects against any site information. So here I only look at its impacts on data utility compared to 2 k-anonymity-based methods, which are random perturbation and location swapping. As we can see from tables, geo-indistinguishable masking yields the smallest distance displaced. And also, as we look at the impacts on cluster detection, we'll see that with reference to the original point data, geo-indistinguishable masking yields high values of precision, recall, and F-scores. These suggest that our methods can effectively preserve the spatial pattern of the data for cluster detection. So the methods we just talked about previously all have the same goal of ensuring anonymity for personal data that involve location information. In fact, in a narrow sense, location privacy is often somewhat equal to anonymity, as we want to prevent surveillance and disclosure of the locations that can be used to identify us. Anonymity is a natural pursuit of humans in modern society, both physically in cities and more generally our living environments, as well as digitally as our lives become increasingly datafied. However, is anonymity all we need for privacy? One counterexample is that predictive models such as AI can now use anonymous training data to infer sensitive attributes about others without consent, such as sexual identity. And although all the data involved here are anonymized, individual privacy is still at risk. Another example that's probably more relevant to geospatial research is geodemographic profiling, which uses clustering to group neighborhoods by similar attributes. And this process also relies on anonymous, often aggregated data. For example, in these geodemographic products produced by a commercial company called Maptitude. We can see clusters of neighborhoods named as comfortable living, affluent environments based on attributes such as income and the percentage of family and so on. However, geodemographic profiling can also pose privacy risk. In geodemographic profiling, individuals often have little or no control over the collection and the use of their data because these data are often gathered from public records, online activities, or purchased from data brokers without their explicit consent. And also, the use of geodemographic profiling can affect individuals' opportunities and choices based on assumptions made about them. In a 1997 paper by Michael Curry, he says that as geodemographic profiling creates data profiles, it constructs a world of virtual individuals for digital puppets, and they raise serious problems for the maintenance of a right to privacy. So because current technology and data can pose privacy risk without using identifiable information, I argue for moving beyond the prevalent individualistic approach to location privacy that emphasizes anonymity to a more collective approach that recognizes the codependency and cooperation in privacy protection. One practical way to achieve this is to shift our focus from personal data to the broader inequalities and risk that data use can pose, such as discrimination, geosurveillance, and so on. And also, we should be aware of the differences in specific applications such as employment and law enforcement due to varying data and actors involved. So this harm-based approach to location privacy also leads me to my research on the positionality and social implications of spatial data science. And specifically, one direction that I'm currently exploring is the fairness and justice in geocomputational methods. So part of my research on fairness in geocomputational methods is still related to geodemographic profiling. Again, geodemographic profiling uses clustering methods to group neighborhoods by similar attributes. But the use of clustering and classification also introduces many critiques. One of them is the concern that the resulted groups and categories are not transparent enough and may exclude important data points, which can create biases and may reinforce inequalities in some cases. So this figure shows more details about geodemographic profiles are created. For each cluster, analysts will typically visualize the distribution of each variable involved in the clustering. And then based on the peak of the distribution, which represents the majority attribute values in a cluster, a textual profile will be assigned to the cluster. And in this example, there are 5 profiles such as resilient Black neighborhoods and urban white educated youth and so on. However, creating geodemographic profiles based on the majority of residents can cause problems because certain subgroups such as racial and ethnic minorities may be systematically excluded from the representation. For example, in the urban white educated youth cluster, we can observe that Black residents are less likely to conform to the profile compared to other racial groups across all the domains of attributes that are used to cluster neighborhoods for the Chicago data. So we ask the question, why does this misrepresentation happen? One reason is that geodemographic profiling still mostly relies on classical clustering methods. For example, one method that's commonly used is k-means. For these classical methods, their goals are pretty similar, which is to optimize the overall dissimilarities within each cluster. In k-means, this will mean to minimize the total cost, which is the sum of distance between each data point and its assigned cluster centroid. However, minimizing total cost does not necessarily mean that the cost is equitably distributed across different subgroups. In this diagram here, we can see in classical k-means, the centroids are closer to subgroups with larger populations. And this means that the cluster is less representative of the minority subgroup. In the case of Chicago, we can divide the neighborhoods into 3 subgroups based on their dominant race. And we can see that using the classical k-means method, Black dominant neighborhoods consistently have higher costs than others. And this means that data points representing Black dominant neighborhoods are typically farther away from their cluster centroid, which indicates potential misrepresentation. So to address this limitation of classical clustering method, we propose a socially fair geodemographic clustering framework. Here, instead of minimizing the total cost, we redesign the objective to minimize the maximum average cost across all subgroups. We also apply this to both crisp and fuzzy clustering, where crisp clustering only assign each neighborhood to one cluster, but in fuzzy clustering, each neighborhood can belong to multiple clusters with multiple degrees of membership. And we show the cost from our socially fair methods using the dotted lines here. As we can see from the results, this new clustering framework can better ensure equitable cost distribution across neighborhoods with different dominant race. And this means that neighborhoods in different subgroups receive more equitable representation from the profile. We also look at fairness issues in optimization problems. Many classical spatial optimization problems are based on the utilitarian principle, which aims to minimize total costs or maximize overall coverage based on factors such as demand, distance, and resource availability. One example of such problems is the maximal covering location problem, or MCLP. And here, in the case of sensor placement, it typically aims to maximize the total amount of population covered by locating a fixed number of sensors. But utilitarian decision is not necessarily a just one. When we place sensors in cities, for example, we need to understand that different populations may have different levels of vulnerability, both physically and socially. In Chicago, minorities and low-income communities have long bear a disproportionate burden of environmental hazards due to redlining, industrial zoning, and urban renewal. So in sensor placement, it would be important to not only consider maximizing the overall coverage, but also equitable coverage across different social groups. So in the preliminary study, I incorporate the equity consideration as an additional objective to the MCLP. And as you can see from the results, the sensor distribution stretches beyond just central Chicago to the south and the west, which historically have a higher concentration of industries and highways. So in summary, in the study I share, in this presentation, I share my research on location privacy and beyond on the ethics, fairness in spatial data science. So I talked about the trade-offs between privacy and utility, especially concerning sensor data privacy protection and also privacy protection for spatial point data. And also talks about the necessity to move beyond anonymity to focus on collective actions and to focus on privacy harms instead of personal data. And moving beyond that, I also look at my research on fairness and equity in spatial data methods. That includes geodemographic clustering, how can that be fair, and also how to incorporate equity and fairness considerations in optimization. So at the end of this presentation, I want to recall Ari Shepard's point that GIS is not a tool, not just a tool, but a social technology with an entire institutional and intellectual infrastructure. As we move beyond GIS into spatial data science and further artificial intelligence, I think it is important to continue reflecting on these emerging technologies, how these emerging technologies shape and are shaped by the society. And it is also important for all of us to understand the social implications of new technologies and think of ways to mitigate these negative impacts. And I will continue to work in this area, and I hope to reach more conversations on this topic. Thank you all for coming, and I welcome any questions.
Thank you, Yue. Any questions for Yue? I think there is one in chat. Yeah, there is a question in chat from Ima.
Yeah, thank you for the question. So if you go back to look at the impact of the census privacy protection methods here. So for the existing privacy protection methods applied by the census, so it has the most significant impact on smaller populations over large populations. So I would say if we just look at the population count, like how detailed each census are about local populations, then we can have a sense of which census is faced more with this kind of trade-offs. So for example, if I know that there are some census data, they're only published for like tract level. So at that geographic level, the impact on the data is not so significant. But if we go down to block group level, for example, then sometimes it's gonna alter the statistics completely. So if we sort of look at what kind of geographic levels each census can go, then we can have a sense of the impact.
Thank you for that. Any further questions for you?
Can I ask out loud rather than
Yes,
put it in the
please.
chat? In your early work, you were examining the trade-off. Early work in this presentation, you were examining the trade-off between utility and privacy. And I'm wondering if both of those things aren't really context dependent. For example, a health application might have different expectations about preservation of things versus some other application. How do you resolve that? Or is it, am I off base? And then I'll be quiet.
Yeah, so I think that's a good question. So there are certain things there are certain concerns that are specific to applications, but in terms of census data, I think a lot of people from different areas, what they really care about is the population totals. Because when we calculate disease rates, for example, the population totals is sometimes just oftentimes involved in that calculation. And if we change the population totals by privacy protection methods, for example, that's going to alter that statistic completely. So in the case of census data, we read a lot of like articles, and then we just sort of decide to just focus on the population totals, how to maintain that statistics, how to not alter that significantly. So that's one way that we define utility. But you're right, if we're working with some other kinds of data, then we should have different context-specific definitions for utility.
Thank you.
Thank you.
This is really interesting and important work. Thank you. And I'm just you do a lot of survey research, and in Utah, which is has very small minority populations. I mean, it's a very white, homogenous population in small towns, but also large cities. And we wrestle with this question a lot. And I guess I'm just asking if you are part of iGuide, if you are interested in working with others who are wrestling with this question, not at the census level, but working with geospatially relevant survey data.
Yeah.
I would just love to get your input.
Yeah, of course. So I think it's in 2022, I was part of the iGuys Community Champions projects, and I developed some tutorials on the platform, on the CyberGIS platforms. And I'm certainly interested in working with local communities to get more perspective from local researchers, and also from survey data. So I think that's also very important and very interesting. And yeah.
Yeah, I think that one of the things that we are in the very early stages of thinking about is redevelopment of a survey data viewer that would allow multiple surveys to be. We have developed this. We developed it 10 years ago, but it really doesn't have any adjustments incorporated for geoprivacy in these unique cases. But if we were to develop that, redevelop that moving forward, these are the kinds of things that I think we must address, and your role would be absolutely pivotal. We do a lot of work to compare our respondents to census data, and this issue makes me wonder, maybe our survey data respondents are actually more representative of what's happening in communities than the census data is, because we work with a lot of small towns. So you've raised a lot of good questions. So I just really appreciate your presentation. Thank you.
Yeah, thank you for the comments. So I think for a lot of survey data, what people commonly do is to do data suppression. So if you end up only having one or two individuals' data, they just decide not to publish it. So I think one reason why the census is using this new method is that they still want to publish it, but they just want to add some uncertainties into it so that we don't just expose people out there. And I think if we want to compare our locally surveyed data with the census data, it is also a good idea to have some understanding about what the census is doing in terms of privacy protection, right? So that we don't sort of compare our raw data with their noisy data. So I think getting to know what the census is doing and how that impact their statistics is also important if we want to make any comparisons.
Yeah, great advice. Thank you.
Mm-hmm.
Can I blurt out something else? So one of the things that I was struck by was your comments towards the end, and I was hearkening back to the early 80s when there was quite a debate about equity versus efficiency.
Mm-hmm.
And that seemed to be very related to what you were saying. And I just wanted to point that out to you so that you might have a look back at that literature if you haven't already. The other thing I was thinking about was, and I also really liked your presentation, by the way. I'm being kind of slightly critical, but I'm engaged because I thought it was very good. So you are envisioning utility and privacy as orthogonal, and that's a good graphical thing to be thinking about in terms of the way you're representing the solution space. But are those two dimensions orthogonal necessarily? Couldn't they be correlated? So rather than being at a 90-degree angle, you're playing around with something else. I don't know. I'm just asking the question. Xiaowen knows how I ask questions.
Yes, thank you for the comments and the question. And so for the first comment, the literature on equity and efficiency, I know that there are lots of literature in spatial optimization and location allocation modeling, and like many decades ago, I've been looking at those literature. So what's new in my current research, I guess, is to incorporate some new thoughts in the social justice literature. For example, intersectionalities and some perspectives from environmental justice. So we're not just like trying to give an equitable distribution for all the social demographic groups. But what we really want to do is to try to address try to cover people with specific needs for the census, for example. So yeah, I think that's one thing that we're trying to do for in terms of the justice and equity and optimization modeling. And also in terms of this graph here, so we so the first thing that I want to say is that we know there is a conflict between privacy and privacy protection and data utility, because we analyzed the mathematical formulation of our objectives. So if we if we assign an individual to another location, then mathematically it's going to decrease the value for data utility. So that's why we say that there should be a trade-off between them, because these two objectives, they're in nature they're conflicted. But as for whether they should be orthogonal, I think that's a good thought, a good question. We didn't get a chance to think about that. Yeah, but I think that's definitely something to think about like in the future.
Thank you for your comments.
Could I ask a question, Anam?
Yes, please.
Well, first, thanks, Julia, for your nice presentation. I really enjoyed it. The work I think you're pursuing is quite interesting, but also important. I was curious about multi-source data. Maybe you have covered this. I was a bit late joining your presentation in terms of the data getting integrated in terms of the privacy protection versus the data utility.
Mm-hmm.
You're trying to balance, especially data coming from non authoritative sources like census data you're looking at. This could be from more targeted surveys Courtney was asking, but also from all sources, social media and so on and so forth. So that's question number one. Question number two, maybe related, but not necessarily, is the emergence of AI approaches introduced to, of course, distorting the data space, especially for multi-source data. That's sometimes actually introducing the benefit for protecting privacy, but certainly it has the other side of the sword, oftentimes exposing more risks to data privacy. I was wondering whether your research has explored that trade-off because of the introduction of AI approaches in this space.
Yeah, so I think these are good questions. Thank you for your questions. So for the first question, the multi-source data, so we've been thinking about that, but as you know, this is a real challenge because one important principle we have in privacy protection or disclosure avoidance is that we're not just trying to provide privacy, we're trying to control the privacy protection levels. And if the data we get, they have different levels of privacy protections, then how do we describe our privacy guarantees? So I think that's one big challenge that we have with multi-source data. And I don't really have like a good answer for that, but that's something that really deserves some thoughts for future research. And for the second question, the AI-based approach, again, we know that the use of AI, because it generates synthetic data, for example, using generative AI, so that can sort of introduce some uncertainties to our data. So that may be a good news if someone cares about privacy protection. But again, the problem is how do we quantify the impacts. How do we quantify the privacy guarantee or any impacts on data utility? So I think for both of these two questions, of course, there are some impacts, but the real problem is how to quantify them. And I think this would be a good a good future direction to work on, to consider these new challenges and new technologies and their impacts on utility and privacy protection.
Thank you. I think in general, good news for you. You got more work to do.
Yeah. Thanks.
Thank you. Any further questions? If not, let's thank our speaker, Yulin, again, and we will make the video as well as the slides available online on the iGuide website.
Thank you.
Thank you all.
Thank you.
Thank you.
Bye.
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 Thank you.